These notes are going to go over bonding. We're going to start mostly talking about ionic bonding, but I'll introduce just a couple of sort of introductory things about bonds in general. So chemical bonds form simply due to an attraction between two atoms or two ions. When it's an attraction between two atoms, this is going to be a covalent bond, which we will talk more about in another set of notes. When the attraction is between two ions, that's going to be an ionic bond, and that's what we're going to be spending the majority of these notes today talking about. So why do bonds form? So the whole goal of forming a bond is so that atoms can fill their valence shell. And for most atoms, they're trying to get to 8 valence electrons. That's the octet rule. Although, remember, helium is an exception. So anybody trying to look like helium, they're trying to get to 2 valence electrons. But otherwise, everybody else is trying to get to 8 valence electrons. And the reason that they do this is because once atoms fill their valence shell, these atoms are less reactive. They are more stable, and they are at a lower energy state, which means that they're less likely to react in another chemical reaction. So just a couple of tidbits that are going to be really important for these sets of notes that we go over for bonding. Just as a reminder, I know we talked about this before, but opposite charges do attract one another. So positive charges are going to attract negative charges. So that'll be like things like protons attracting electrons, or positively charged ions attracting negatively charged ions, whereas like charges will repel. So again, example of this is negative charges will repel other negative charges. That comes into play when we get into our covalent bonds, especially because we'll have electrons that do repel other electrons. So moving forward, our type of bond that forms between two atoms or two ions can often be explained by electronegativity. And we did talk about electronegativity last week, but I will also review some of that information as well, and how it plays a role in the types of bonds that we see here. So electronegativity is the tendency of an atom's nucleus to attract, and we're going to say valence electrons again. And again, when we get to a more refined definition, this will start to turn into a shared pair of electrons. But for now, you can just think about it as an attraction from the atom's nucleus to the electrons, specifically the valence electrons. And this can be their own electrons, so how attracted they are to their own electrons, or even how attracted they are to another atom's electrons. And that's going to play a role in our ionic compounds. Now, as a reminder, electronegativity's trend is that it increases as we move up the periodic table and as we move to the right. So I'm going to draw that onto my picture real fast. So as we move to the right, our electronegativity is increasing. And as we move up our periodic table. So the trend is basically in this direction as we move sort of diagonally from the lower left-hand corner to the upper right-hand corner. Now, since it's all based off of Coulombic attraction, technically ionization energy, which I'll bring up just sort of here and there as we're talking about our ion formation, ionization energy also follows the same trend. So it is also increasing as we move from left to right and as we move up our periodic table, right? Because that all has to do with how attracted the nucleus of the atom is to the valence electrons. As a reminder, ionization energy is specifically the amount of energy required to remove valence electrons. So basically, if you're really attracted to your valence electrons, it's going to take a lot of energy to remove them. If you are not very attracted to your valence electrons, it will not take very much energy to remove them. I did mention this before. Sometimes people refer to fluorine as flow and state that flow is greedy, whereas Frank over here, Frank is fat, And the idea behind that is Frank is a really big atom, meaning his valence electrons are really far away. And since his valence electrons are so far away, he's not very attracted to them, so his electronegativity is going to be low, which means that his ionization energy would also be low because it wouldn't take very much energy to pluck one of his valence electrons off. Whereas Flo is greedy, so Frank is fat, so Frank has a low electronegativity and a low ionization energy. Flo is greedy, meaning that she's really attracted to her valence electrons. So that means that she has a really high electronegativity, which means that it would be really hard to pluck an electron off. So she also has a really high ionization energy. And this table right here is all electronegativity. So these are the electronegativity values. So when I look at it, I can see that Frank's electronegativity value of 0.7 is actually considerably lower than fluorine, whose electronegativity value is 4.0. So fluorine does have a very high electronegativity. And you will see that the general trend is as you move up, those electronegativity numbers are increasing. And generally, as you move to the right, you will also see that those electronegativity numbers are increasing, fluorine having the highest electronegativity value of all. All right, so just a quick review of that. So we're going to go into our first type of bond, which are going to be ionic bonds. So that's the first one that we're going to learn about. So ionic bonds are the attraction between a cation, that's a positively charged ion, and an anion, which is a negatively charged ion. For us, that's going to be a metal bonded to a nonmetal for the most part. And that makes sense because when I look at my metals, remember family 1 is a 1+, family 2 was a 2+. Aluminum down, because there's a staircase right here, aluminum down is a 3+. These in the transitional metal area, this dip right here, they don't follow a trend, but they do all form cations of some sort. These fellas or atoms over here, these elements also form cations. So all of our metals form cations. Whereas our nonmetals, when we look at our periodic table, remember nitrogen down was a 3-, oxygen down was a 2-, and fluorine down was a 1-. Our nonmetals often form our anions. So it really is going to be a metal that is then going to be attracted to a nonmetal, and that'll be the easiest way to identify our ionic compounds. This ends up happening because the metal will end up losing valence electrons to the nonmetal, which is then going to gain valence electrons. So I've got a little picture of this down here. So here is my example. I use sodium chloride. It's a pretty standard ionic compound. Sodium being my metal, chlorine being a nonmetal. Sodium has an atomic number of 11, which means 11 protons and 11 electrons to start with. Chlorine, 7 protons, and then 17, and then 17 electrons. And what ends up happening is that the valence shell for sodium ends up with just 1 valence electron. So we have just 1 valence electron. Chlorine, on the other hand, has 7 valence electrons. So chlorine wants to gain 1 more, and sodium actually wants to lose 1. So sodium's going to give up that valence electron to chlorine. When we think about electronegativity too, metals tend to have a low electronegativity, meaning that it's easy, it'll give up valence electrons easily, whereas nonmetals have a very high electronegativity, meaning that it won't give up valence electrons, meaning that it's so attracted to electrons that they're more likely to take valence electrons from other atoms. So what ends up happening here is sodium, with its low electronegativity, its valence electron gets taken by a nonmetal who has a high electronegativity. And when I look at my electronegativities, I can see sodium is at 0.9, chlorine is at 3.0. They do have a significantly different a significantly large difference in electronegativities, right? So sodium's is really low, whereas chlorine's is considered very high. So chlorine steals the electron away. That means that sodium now has 10 electrons total, but a full valence shell, right? So it's happier, it's more stable, whereas chlorine now has 18 total electrons, and it also has its full valence shell, so it's also more stable and happy. But when it does that, sodium ends up with a positive charge because it's given up an electron, right? And chlorine ends up with a negative charge because it's taken an electron. So what ends up happening is the sodium and the chlorine, because of those opposite charges, they attract one another and they form an ionic compound, which is a net neutral compound. So the result of an ionic bond is the formation of an ionic compound. And just to sort of reiterate, your ionic compounds are going to be net neutral, which means basically that our cations and our anions are going to attract one another until there is no more charge left, and they're net neutral, because once you're neutral, you're not attracting any more ions towards you. So some other examples of this, I've got off the top of my head, you've got rubidium fluoride, lithium oxide is a nice one to think about. So again, lithium makes a 1+ ion, oxygen makes a 2- ion, so they're not quite net neutral until you add in another lithium here. And so now this is a net neutral compound, and it's our cations over here. So here are our metals, and they are attracting our nonmetals until you form that net neutral compound. Another one is magnesium chloride. Similar idea, magnesium is a 2+ metal. Chlorides ions form a 1- ion, so you're actually going to need two of them to eventually form your net neutral compound. And if you want to look at this more like the sodium and the chloride example, magnesium has 2 valence electrons, whereas each chlorine had 7 valence electrons. These little dots are electrons. We'll talk more about the dots later. But magnesium wants to give up its electrons, so each chloride actually just takes 1, right? And then this forms a 2+. Each of these form a 1-. And then this whole thing, they end up attracting one another and forming a net neutral compound. So that's what's happening in ionic compounds. Our next set of notes will go over covalent bonds.